A burst of electromagnetic radiation arrived from a source roughly 50,000 light-years away from a magnetar designated SGR 1806-20, a dead star roughly 20 kilometers across, and in a fifth of a second it released more energy than our Sun emits in a quarter of a million years. The pulse was so energetic that it briefly ionized the upper layers of Earth's own atmosphere, at altitudes where the air is already so thin it barely exists. Researchers monitoring the ionosphere watched its night side behave like day side for several minutes, from 50,000 light-years away. This was not a black hole. This was a neutron star. The distinction matters. We speak of black holes with a kind of reverential dread, as if nothing in the universe could be more extreme, as if they represent the final word on what matter can become. But neutron stars occupy a stranger frontier. They are not the ending. They are the edge, the last territory where matter still exists in any recognizable form, where the laws of physics reach their absolute limit without quite breaking. They are the borderland between matter and oblivion, and everything we know about the deep nature of reality is either confirmed or challenged somewhere inside them. We still cannot say with certainty what hides at their centers. No theory is complete enough to tell us. In this sense, a neutron star is not just an exotic object. It is an open question written in compressed stellar fire, spinning in the dark, waiting for us to become clever enough to read it. The story of how we came to know these objects exist is itself a kind of detective story. In 1934, astronomers Walter Baade and Fritz Zwicky proposed with remarkable foresight that supernova explosions might leave behind ultra-compact stellar remnants composed primarily of neutrons. This prediction was made just 2 years after the neutron itself was discovered. At the time, it seemed almost entirely theoretical, a mathematical possibility rather than a physical reality. No instrument existed that could have detected such an object at interstellar distances, and the proposal was regarded by many colleagues as speculative to the point of fantasy. It would sit largely unverified for more than 3 decades. Then, in the summer of 1967, a graduate student at Cambridge named Jocelyn Bell was analyzing paper readouts from a radio telescope she had helped build, scanning for something else entirely, when she noticed a repeating signal she could not explain. It pulsed every 1.33 seconds with a regularity that exceeded the accuracy of most clocks. The signal was so precise that the team briefly and seriously entertained the possibility it was artificial, a beacon from an extraterrestrial intelligence. They designated it LGM-1 for Little Green Men. Within months, however, several more of these sources were discovered in different parts of the sky, and the alien hypothesis became untenable. What Bell had found were pulsars, rapidly rotating neutron stars, sweeping beams of radio emission across space with every turn. Baade and Zwicky had been right. The objects were real. The recognition of pulsars as rotating neutron stars came quickly once the theoretical machinery was assembled. Thomas Goad at Cornell proposed the rotating neutron star model in 1968, and the identification of a pulsar at the center of the Crab Nebula, a known supernova remnant, essentially confirmed it. A dead star was sitting at the center of a 1,000-year-old explosion, exactly where the theory said one should be. Astronomy does not often offer such clean confirmations, and the community absorbed the result with something approaching disbelief, followed by wonder. To understand how such objects come to exist, we need to follow a massive star through its final hours. Stars of sufficient mass, roughly 8 times the mass of our Sun or greater, spend their lives fusing progressively heavier elements in their cores. Hydrogen becomes helium, helium becomes carbon, carbon becomes neon, then oxygen, then silicon. Each stage proceeds more quickly than the last, because heavier fusion requires higher temperatures and more energy to sustain, but releases proportionally less of it. The silicon burning phase that produces iron lasts on the order of days in a star, many times the sun's mass. When the core fills with iron, everything stops. Iron sits at the bottom of the nuclear binding energy curve. It cannot release energy through further fusion, and it cannot release energy through fission. It is the dead end of stellar nucleosynthesis. The iron core, suddenly unsupported by outward pressure, collapses. It does so in less than a second. A core that was roughly the size of Earth shrinks to a sphere 10 or 15 kilometers across in the time it takes you to read this sentence. The compression squeezes electrons into protons, producing neutrons and neutrinos in enormous quantities. The infalling outer layers of the star slam into this newly formed dense core at a significant fraction of the speed of light, rebound in an enormous shock wave, and explode outward into space. This is a core collapse supernova. The explosion is visible across galactic distances. It outshines every other star in the galaxy that contains it, sometimes for weeks. And what remains at the center, if the mass of the collapsing core falls within a certain range, is a neutron star. The precise mechanism by which the stalled shock wave is revived and driven outward against the infalling stellar material remains one of the central unsolved problems in computational astrophysics. The shock forms when the rebounding core material slams into infalling matter, but within milliseconds it stalls, losing energy to photodissociation of infalling iron nuclei. Something must revive it. The leading candidate is neutrino heating. The enormous flood of neutrinos produced in the core deposits a small fraction of its energy into the shock region, enough to restart the outward expansion. Turbulence, convective instabilities, and a phenomenon called the standing accretion shock instability, a large-scale sloshing of the shock front, all appear to play roles in making the explosion succeed, rather than simply fall back onto the core and collapse to a black hole. Three-dimensional simulations of core collapse supernovae are among the most computationally demanding calculations in science, and they still cannot fully replicate the observed explosion energies for all progenitor masses. The supernova engine is still being understood. The newborn neutron star is, in its first moments, one of the hottest objects in the universe. Internal temperatures reach somewhere between 50 and 100 billion degrees Celsius. This is hotter than any living star, hotter than most supernova explosions. But the star cannot hold this heat for long, and the mechanism by which it loses it is extraordinary, rather than radiating from its surface. As ordinary hot objects do, a young neutron star cools from the inside out by producing an enormous flood of neutrinos. Neutrinos are particles that interact with matter so weakly that a light year of lead would only stop about half of them. They pass through the neutron star's body almost unimpeded and carry enormous quantities of energy into space. In the first 10 seconds after a neutron star's burst, the neutrino emission is so intense that the flux of these particles briefly exceeds the combined luminosity of all the stars in the observable universe. This process has been observed at least once in real time. In February 1987, a star in the Large Magellanic Cloud exploded as SN 1987A. Neutrino detectors buried deep underground in Japan and in North America registered a pulse of neutrinos a few hours before any optical brightening was seen on Earth. This sequence confirmed the theoretical picture. The collapse happens first, the neutrinos escape immediately, and the visible light of the explosion only arrives after the shock wave has had time to travel through the star's outer layers and break through the surface. Those detectors captured roughly 20 neutrinos from an event 160,000 light years away. 20 particles out of the 10 to the 58 power emitted. Even so, it was enough. The three neutrino detectors that recorded SN 1987A were Kameokan did second in Japan, the Irvine, Michigan Brookhaven detector in the United States, and the Baksan scintillation telescope in the Soviet Union. Their results agreed. The neutrino burst lasted approximately 12 seconds, consistent with the Kelvin-Helmholtz cooling of a hot proton-neutron star, and its total energy was consistent with the conversion of roughly a tenth of a solar mass of material into gravitational binding energy. The signal was faint, a handful of events above background in each detector, but it carried enough information to confirm the theoretical picture of stellar core collapse that Bade, Zwicky, and generations of subsequent theorists had built. SN 187A remains the only supernova from which neutrinos have been directly detected, and the remnant is still being monitored today as it expands and brightens in radio waves and X-rays, sweeping up circumstellar material the progenitor star expelled centuries before its death. The historical record of supernovae visible to the naked eye stretches back to antiquity. Chinese and Arab astronomers recorded a brilliant new star in 106 CE that appeared in the southern sky in the constellation Lupus. It was so bright at its peak that it cast shadows at night. Medieval documents describe it as having the brightness of a quarter moon. SN 1006, as it is now designated, occurred roughly 7,000 light-years away. The expanding remnant is still visible today as a radio and X-ray source, a thin shell of shocked gas 260 light-years across, still expanding at roughly 3,000 kilometers per second after more than 1,000 years. In 1572, Tycho Brahe observed a new star in Cassiopeia, bright enough to be seen in daylight. Its steady brightness, unchanging against the backdrop of fixed stars, directly contradicted the Aristotelian cosmology of the era, which held that the heavens were immutable. Tycho's supernova, SN 1572, was followed in 1504 by Kepler's supernova in Ophiuchus, which remained visible to the naked eye for about a year. These historical events demonstrated that the cosmos was not static, that catastrophic changes could occur at stellar distances, and that the sky was a record of violence as much as of permanence. As a neutron star ages, its cooling slows and its surface behavior becomes increasingly strange. In 2010, astronomers using the Chandra X-ray Observatory monitored the neutron star at the center of Cassiopeia A, the youngest known neutron star remnant in our galaxy, formed by a supernova that occurred around the year 1681. Over a decade of observation, the surface temperature of Cassiopeia A's neutron star dropped measurably by roughly 4%. This is not a small number for a star. It suggested that neutron superfluidity had recently switched on in the interior, a transition in which neutrons in the core began to form quantum mechanical pairs, called Cooper pairs, fundamentally changing the thermal properties of the deep interior. It was the first direct observational evidence for neutron superfluidity inside a neutron star, a quantum effect operating inside an object heavier than the Sun. The cooling of neutron stars is not uniform. Theoretical models predict two distinct regimes depending on whether the so-called direct Urca process can operate in the core. In this process, a neutron decays into a proton, electron, and antineutrino, and the proton then captures an electron to become a neutron again, with each cycle emitting neutrinos. If the proton fraction in the core exceeds a certain threshold, this process is allowed and the neutron star cools dramatically faster than standard models predict. If the proton fraction falls below the threshold, the direct Urca process is forbidden by momentum conservation and cooling proceeds through slower modified Urca processes. Whether a given neutron star's core is above or below this threshold depends on the equation of state. Observations of surface temperatures of neutron stars of known ages therefore provide a way to constrain the equation of state from the outside. Some neutron stars appear to be cooling faster than the standard model predicts. Others cool more slowly. The spread in observed cooling rates suggests that neither the direct Urca process nor superfluidity is universal. that the internal structure of neutron stars varies significantly depending on their mass and possibly on details of how they were born. Imagine descending into one of these objects. The descent begins at the surface, which is not what intuition would suggest. There is an atmosphere, though, calling it that feels almost ironic.
It is a layer, perhaps a few centimeters thick, composed of the lightest available elements, hydrogen, helium, perhaps carbon, held against the surface by gravity roughly 200 billion times stronger than Earth's. Below this thin film of gas, the crust begins. The outer crust is composed of iron nuclei arranged in a crystal lattice, so ordered and so compressed that it forms the stiffest material in the known universe. A cubic centimeter of this outer crust, brought to Earth, would weigh roughly 1 million tons. The composition of the atmosphere has real consequences for what we observe. A hydrogen atmosphere radiates differently from a carbon atmosphere or a naked iron surface. The spectrum of a neutron star's thermal emission, as measured by X-ray telescopes, is shaped by whatever elements are present in its outermost layers. Heavier elements produce broader, more complex spectral features. Lighter elements produce cleaner blackbody-like emission. For most isolated neutron stars, the atmosphere is believed to be hydrogen or helium, because gravity stratifies elements so rapidly that any heavy material sinks out of the photosphere in days or weeks. But in a neutron star that has undergone significant thermonuclear burning on its surface, the dominant atmospheric element may be carbon, left behind after hydrogen and helium have been consumed. The inferred atmospheric composition affects the derived surface temperature and radius, which in turn constrains the equation of state. Getting the atmosphere right is not a cosmetic detail, it is load-bearing for the physics. Deeper, the increasing pressure forces nuclei to absorb electrons in a process called inverse beta decay, converting protons to neutrons. Nuclei become progressively more neutron-rich as you descend, growing larger and less stable than any nucleus that has ever been observed in a terrestrial laboratory. Below a certain depth, the neutrons begin to leak out of nuclei entirely, forming a superfluid of free neutrons that flows through the lattice of nuclei without friction. This is the inner crust. It is a material that exists nowhere else. Go deeper still, and the nuclear structures dissolve into a regime that physicists have taken to calling nuclear pasta. Not as a joke, though the names are earnest. At densities approaching nuclear saturation density, roughly 300 million billion grams per cubic centimeter. The competition between the nuclear attractive force and the electromagnetic repulsive force causes matter to arrange itself into elongated tubes called spaghetti, flat sheets called lasagna, and interconnected networks called gyroid phases before dissolving entirely into a uniform fluid. These pasta phases are predicted to be the strongest materials in the universe. A crust of nuclear pasta would require forces roughly 10 billion times greater than those needed to deform steel to break it. Its elastic properties influence how neutron stars vibrate when they are disturbed by quakes or tidal forces. Measuring the vibrational modes of neutron stars, seismology at stellar scale, is a direct probe of the pasta structure, and the quasi-periodic oscillations observed in the X-ray emission following magnetar giant flares may be exactly this, the ringing of a neutron star's crust after a catastrophic fracture. Below the pasta, the neutrons and protons form a dense liquid. The behavior of this liquid is described by what physicists call the equation of state, a mathematical relationship between the pressure, density, and temperature of the material. Finding the correct equation of state for dense nuclear matter is one of the central unsolved problems in theoretical physics. Different proposed equations of state predict neutron stars of different radii. If the equation of state is stiff, meaning the material resists compression strongly, neutron stars should be larger, roughly 13 or 14 kilometers across. If it is soft, they should be smaller.
Measuring actual neutron star radii, therefore, is a direct test of nuclear theory at densities and pressures that no accelerator on Earth can replicate. The nuclear symmetry energy is a key quantity in this problem. It describes how much the energy of nuclear matter changes as the proportion of neutrons to protons is varied away from equal numbers. Neutron stars are almost entirely composed of neutrons, making the symmetry energy directly relevant to their structure. Experiments at heavy ion accelerators bombarding lead nuclei with each other at various energies, measuring the distribution and velocity of the debris, have begun to constrain the symmetry energy in the laboratory. The lead radius experiment at the Jefferson Laboratory measured the neutron skin thickness of lead-208, the extra extent of the neutron distribution beyond the proton distribution, and found it to be about 0.28 millimeters in nuclear units, slightly larger than some models had predicted. A thicker neutron skin corresponds to a stiffer symmetry energy, which in turn predicts larger neutron star radii. The connection between a nuclear physics measurement performed in a terrestrial laboratory and the size of a dead star 20 kilometers across is direct and quantitative, and the results from these experiments are being incorporated into the same theoretical frameworks that describe what happens inside neutron stars. This is the scientific mission of NICER, NASA's Neutron Star Interior Composition Explorer, a compact telescope mounted on the International Space Station since 2017.
NICER measures X-ray pulses from rotating neutron stars with extraordinary timing precision, tracking hotspots on their surfaces as they rotate in and out of view because general relativity bends the path of the X-rays as they travel away from the star. The shape of the pulse profile encodes information about the stellar radius. By analyzing these profiles, NICER has placed the first genuine observational constraints on neutron star size. The current best estimates suggest a typical neutron star of about 1.4 solar masses has a radius somewhere between 11 and 13 kilometers. This is consistent with the moderately stiff equation of state, but the uncertainties remain large enough to leave the deepest questions open. Theoretical models suggest that near the center of a massive neutron star, the pressure becomes sufficient to dissolve protons and neutrons entirely into their constituent quarks. If this is correct, then the core of a neutron star contains quark matter, a state of matter that has never been directly observed and may be the only place in the current universe where it exists in bulk at low temperature. At accelerator experiments like the Large Hadron Collider, quark-gluon plasma has been produced for fractions of a second at temperatures of several trillion degrees. But the quark matter proposed inside neutron stars would exist at much lower temperatures and far higher densities, a regime that cannot be reached in any experiment. The quarks would be cold and dense, potentially forming what theorists call a color-flavor locked phase, a state with properties so unusual that even its electromagnetic behavior would be different from anything we have encountered. Other models propose the formation of condensates of kaons or hyperons, heavier relatives of protons and neutrons, which carry strangeness, a quantum number associated with strange quarks. We genuinely do not know which picture is correct. We may not know for decades. Every neutron star is a sealed laboratory running an experiment we cannot yet fully interpret. One of the more surprising features of neutron stars is what lies just beneath the surface. In young neutron stars, and in those that are actively accreting material from a companion star, a layer of liquid exists between the ridged crust and the deeper interior. This is not water, it is a fluid composed of atomic nuclei, predominantly carbon if significant thermonuclear burning has occurred, suspended in the free electron sea. The density of this ocean is tens of millions of times greater than the density of water. Its depth is comparable to shallow coastal seas on Earth. Yet it wraps entirely around an object the size of a city.
Within this liquid, heavy elements settle rapidly under the intense gravitational field, stratifying by mass in a matter of days or weeks. The lightest elements float at the top. The heaviest sink without hesitation in accreting neutron stars. This ocean becomes the stage for some of the most energetic phenomena in the galaxy. When a neutron star in a binary system draws hydrogen and helium from its companion, that material accumulates on the surface. Under the combined pressure and heat of the neutron star's gravity, it compresses until it crosses the ignition threshold for thermonuclear fusion. The flash is not gradual. It propagates across the stellar surface as a burning front, a wave of thermonuclear fire racing around a sphere 10 kilometers across. The whole event lasts roughly a minute. In that minute, the neutron star releases as much energy as the sun produces in an entire year. These X-ray bursts repeat in some systems with regularity. In rare systems, something even more extreme occurs: a superburst, a thermonuclear flash from the carbon layer deep in the ocean, lasting hours rather than minutes, releasing 1,000 times the energy of an ordinary burst. The ocean itself ignites. The neutron stars that produce X-ray bursts are components of what astronomers call X-ray binary systems, pairs of stars in which a compact object, neutron star or black hole, accretes matter from a companion. Among the neutron star X-ray binaries, there are two broad families. High-mass X-ray binaries pair a neutron star with an OB supergiant or B star, transferring matter through a stellar wind or from the equatorial disk of a rapidly rotating companion. These systems tend to show X-ray pulsations because the neutron star has a strong magnetic field that channels the accreted material onto magnetic poles, producing hotspots that rotate in and out of view. Low-mass X-ray binaries pair a neutron star with a sun-like or smaller companion, transferring matter through Roche-Lobe overflow. The gradual spilling of the companion's atmosphere over the gravitational boundary between the two stars. These systems often do not show persistent pulsations because the neutron star's magnetic field has been buried and weakened by decades or centuries of accretion, smoothing out the hotspots. Scorpius X1, detected in 1962 in the first X-ray astronomy observation ever conducted from a rocket, is the brightest persistent X-ray source in the sky outside the solar system, and is a classic low-mass X-ray binary. Its neutron star accretes at close to the maximum possible rate, near the Eddington limit for X-ray luminosity. Hercules X1, discovered in 1972, is a high-mass X-ray binary whose neutron star pulses every 1.24 seconds and whose accretion disk precesses on a 35-day cycle, periodically blocking our view of the source. These two systems, studied for decades, established the basic phenomenology of X-ray binary accretion and provided the first convincing cases for neutron stars in binary systems outside the pulsar context. The magnetic fields of neutron stars span a range that staggers imagination. An ordinary pulsar carries a surface magnetic field of roughly 1 trillion Gauss. For reference, the strongest sustained magnetic field produced in any terrestrial laboratory is around 45 Tesla or 450,000 Gauss. A pulsar's field is roughly 1 billion times stronger than that. But magnetars occupy a different category entirely. Their fields reach 10 to 100,000 trillion Gauss, strong enough that if a magnetar were placed halfway to the moon, it would erase every credit card on Earth, alter the orbital electrons of atoms in your body, and distort the geometry of your molecules. At such field strengths, the vacuum itself becomes birefringent. Light polarized parallel to the field and light polarized perpendicular to it travel at slightly different speeds, an effect called vacuum birefringence that was first proposed by quantum electrodynamics and was detected for the first time in 2017 in observations of the neutron star RX. J100 856.53754 using the European Southern Observatory's Very Large Telescope.
Magnetars fall into two observational classes, which were originally discovered and named independently before their connection was understood. Soft gamma repeaters are sources of repeated outbursts of gamma ray and X-ray emission, detected primarily during episodes of enhanced activity. Anomalous X-ray pulsars are slowly rotating neutron stars with periods of several seconds rather than milliseconds that are too bright in X-rays to be powered by rotation alone, requiring an additional energy source. By the mid-1990s, theorists had proposed that both classes were magnetars, neutron stars whose decay of an extraordinarily strong magnetic field rather than rotation or accretion powered their emission. The theory was resisted for years, partly because it required magnetic fields stronger than many physicists believed plausible, but the observational evidence gradually accumulated until the identification became accepted. Today, around 30 magnetars are known in the Milky Way, out of an estimated total population of millions of neutron stars. Magnetar outbursts, like the one from SGR 8NO620 in 2004, release their energy through a sudden rearrangement of the magnetic field, a starquake. The crust of a neutron star is not perfectly rigid. As the star slowly loses rotational energy and its internal structure adjusts, stresses accumulate in the crust until it fractures. On Earth, crust fractures release energies measured in the billions of joules. On a magnetar, the same event can release more energy in a fraction of a second than the Sun will emit in 10,000 years. The 2004 flare was detected by spacecraft at Mars, Saturn, and at Earth. It was not the first such event. In 1979, a similar burst from SGR 052666 in the Large Magellanic Cloud briefly saturated every gamma-ray instrument in space. Following magnetar giant flares, X-ray observatories have detected quasi-periodic oscillations in the decaying emission. Rhythmic pulsations at frequencies of tens to hundreds of cycles per second, lasting for minutes after the initial burst. These oscillations are thought to be the ringing of the neutron star's crust, torsional seismic waves bouncing back and forth through the rigid nuclear lattice, excited by the catastrophic fracture that triggered the flare. The frequencies of these oscillations encode information about the elastic properties of the crust, the composition of the nuclear pasta layers, and the shear modulus of the nuclear lattice. Magnetar seismology is a young field, but its potential is significant. Just as terrestrial seismology revealed the layered structure of the Earth's interior, stellar seismology may allow us to map the interior of neutron stars using the vibrations they produce when they shatter. There is a subclass of neutron stars that connects magnetar activity to one of the most puzzling phenomena in contemporary astrophysics. Fast radio bursts are millisecond duration flashes of radio emission so bright they can be detected from billions of light years away. Their origin remained unknown for over a decade after their discovery in archival data in 2007. In April of 2020, a fast radio burst was detected coming from inside the Milky Way itself, from the direction of the magnetar SGR 1935 plus 21154. At almost exactly the same moment, X-ray observatories detected a burst from the same source. For the first time, a fast radio burst had been caught in the act and linked to a known object. The mechanism is still debated, but the association with magnetars is now considered the leading explanation. Inside these tiny, violently magnetic objects, something shakes the magnetic field so severely that it launches a wave of coherent radio emission bright enough to reach across a significant fraction of the observable universe. A dead star the size of a small city shouts loudly enough to be heard from the other side of the cosmos. Some fast radio bursts repeat. Others, as far as we can tell, do not The repeating sources allow detailed study of their emission properties and their local environments. The source FRB 2012 MON110-2A, the first repeating fast radio burst discovered, sits inside a dwarf galaxy roughly 3 billion light-years away in a region of intense star formation, near what appears to be a persistent radio source, possibly the nebula, surrounding a young, highly active magnetar. The non-repeating sources may be single catastrophic events. Magnetar giant flares from distant galaxies, neutron star mergers, or some other transient process that destroys or exhausts the emitting system. The taxonomy of fast radio bursts is still being written, and the answer may turn out to be that there is more than one type of source producing similar-looking signals by different mechanisms. The universe rarely gives us the luxury of a single explanation. A neutron star rotating rapidly and emitting focused beams of electromagnetic radiation is called a pulsar. The beams sweep across space as the star rotates, and if Earth lies in their path, we detect regular pulses. The Crab pulsar, embedded in the remnant of the supernova observed in 1054 AD by Chinese and Arab astronomers, rotates 30 times per second. It powers its surrounding nebula with a wind of particles and fields so energetic that the Crab nebula shines brightly in X-rays, gamma rays, and visible light, and has for nearly 1,000 years. The pulsar is not simply sitting there rotating, it is braking. Its rotation slows measurably from year to year as the magnetic braking steals angular momentum. The energy extracted from the Crab pulsar's rotation is deposited into the surrounding nebula as a pulsar wind, a relativistic outflow of electrons, positrons, and electromagnetic fields. This wind slams into the surrounding supernova ejecta at the termination shock, a standing shock wave where the wind's kinetic energy is converted into high-energy particles. These particles spiral in the nebular magnetic field and radiate synchrotron radiation across the electromagnetic spectrum. The Crab Nebula is so well studied at so many wavelengths that it is used as a calibration source for X-ray telescopes. When an X-ray observatory needs to verify its sensitivity, it points at the Crab. A supernova remnant nearly 1,000 years old serves as an engineering reference standard for 21st century instruments. Pulsars do not always slow smoothly. Occasionally, a pulsar will suddenly speed up, a brief acceleration known as a glitch. The Vela pulsar, rotating about 11 times per second and sitting roughly 1,000 light-years away in the constellation Vela, glitches roughly every 3 years. Each glitch is small in absolute terms. The fractional change in rotation rate is on the order of a millionth, but it is sudden, happening in less than a minute, and followed by a slow relaxation lasting weeks to months. The leading explanation is that glitches are caused by the neutron superfluid inside the crust becoming momentarily coupled to the rigid crust. Transferring some of its angular momentum, the superfluid, unimpeded by friction, stores its rotation rate while the crust slows under magnetic braking. Periodically, the coupling snaps into place and the crust is briefly spun up. If this picture is correct, pulsar glitches are the only observable astronomical phenomenon directly caused by a quantum superfluid operating inside a stellar object. They are quantum mechanics at stellar scale. Some pulsars push timing precision to extraordinary extremes. Millisecond pulsars rotate hundreds of times per second. Their pulse is so regular they rival atomic clocks. These objects have typically been spun up by accreting matter from a companion over millions of years, gaining angular momentum until they spin at rates that would destroy any less compact object. PSR J1748-2446 AD in the globular cluster Tarzan 5 in Sagittarius rotates more than 700 times per second. Its equatorial surface moves at roughly a quarter of the speed of light. The timing stability of millisecond pulsars is so precise that arrays of them, pulsar timing arrays monitored by radio telescopes across multiple continents, are now being used as a gravitational wave detector in their own right. In 2023, pulsar timing arrays in North America, Europe, China, India, and Australia simultaneously announced evidence for a gravitational wave background, a low-frequency hum of gravitational waves permeating all of space, almost certainly produced by the population of supermassive black hole binaries scattered across the universe. The signal was found not with mirrors and lasers, but with dead stars spinning in distant globular clusters, whose pulses carry the imprint of space-time's trembling. The transition from accreting neutron star to millisecond pulsar is not merely theoretical, it has been caught in action. A class of systems called transitional millisecond pulsars switches between two modes of behavior on timescales of weeks or months. In the accretion mode, the system appears as a bright X-ray source, with matter flowing from the companion onto the neutron star. In the rotation-powered mode, the accretion stops. The matter is driven away by the pressure of the pulsar's radiation and wind, and the neutron star appears as a radio millisecond pulsar. PSR J1023 plus 0038 in the constellation Sextans has been observed to switch between these states multiple times, providing direct evidence that the spin-up of millisecond pulsars by accretion is an ongoing process in the current universe, not just a historical relic. The transitional systems are rare, only a handful are known, but they represent a brief observable moment in a multi-million-year evolutionary process that converts slow, highly magnetized pulsars into fast, weakly magnetized millisecond pulsars through a prolonged period of accretion. The companion donates its outer layers to spin up the dead star and is itself slowly eroded in the process. Binary pulsars provide the most precise tests of general relativity available outside the solar system. In 1974, Russell Holtz and Joseph Taylor discovered a pulsar, PSR B-Mund 1913+16, in a binary system with another neutron star. The system is compact enough that general relativistic effects are measurable. The orbit precesses, time dilation is observable, and most crucially, the orbital period decreases over time as the system loses energy to gravitational wave emission. The measured rate of orbital decay matches the prediction of general relativity to within a fraction of a percent and has done so consistently over decades of observation. Holtz and Taylor were awarded the Nobel Prize in Physics in 1993 for this discovery, the first indirect confirmation that gravitational waves exist. The measurement was not a detection of gravitational waves themselves, but a confirmation that they were being emitted at precisely the rate that general relativity predicted, draining energy from the binary orbit. In 2003, astronomers discovered PSR J0737-3039, the only known binary system in which both members are detectable as pulsars. One pulsar rotates 22 times per second, the other, which receives the wind of particles from the first, rotates about once every 2.8 seconds. The existence of two pulsars in the same binary allows a battery of general relativistic tests that would be impossible with a single pulsar. The Shapiro delay, the slowing of the pulsar's radio signal as it passes through the curved space-time near the companion, the orbital decay, the precession of each pulsar's spin axis, the gravitational redshift of the pulse timing, all are measurable and all agree with general relativity. The system is also physically remarkable. The two neutron stars orbit each other every 2.4 hours, and they will merge in roughly 85 million years, producing a gravitational wave event and a kilonova. Astronomers have already calculated when this will happen and what it will look like.
We will not be here to see it, but the calculation itself is a testament to how well this particular sealed laboratory has been opened.
When two neutron stars orbit each other in a closed binary system, they radiate gravitational waves continuously. Over time, this radiation carries away angular momentum, and the orbital separation shrinks. The inspiral can take hundreds of millions of years, but it ends suddenly. The two stars collide and merge in a catastrophic event lasting milliseconds. In that collision, conditions arise that exist nowhere else in the observable universe. The density briefly exceeds that of any single neutron star. The temperatures spike to values not seen since the first fractions of a second after the Big Bang. And from this chaos, the universe forges its heaviest elements. The first direct detection of a neutron star merger was made on August 17, 2017, when the LIGO and Virgo gravitational wave detectors registered a signal designated GWU 170817 from a source approximately 130 million light-years away in the constellation Hydra. Unlike the four prior gravitational wave detections, all of which came from merging black holes, this one was followed 2 seconds later by a short gamma-ray burst detected by the Fermi Space Telescope and the Integral Satellite. The gamma-ray burst, designated GRB 170817A, was unusually faint compared to typical short gamma-ray bursts. This was explained by the geometry of the event. The relativistic jet that produces the burst was pointed slightly away from Earth, and we were seeing the off-axis emission rather than the beam itself. As the jet expanded and slowed, it swept up interstellar material and produced an afterglow in X-rays and radio waves that gradually brightened over weeks, as the relativistic cone widened enough to include our line of sight. The source had a counterpart in visible light. For the first time in history, astronomers observed the same astronomical event simultaneously in gravitational waves, gamma rays, X-rays, ultraviolet light, visible light, infrared light, and radio waves. The era of multi-messenger astronomy had begun at a specific moment, on a specific morning, with a specific dead star collision in a specific elliptical galaxy. Short gamma-ray bursts, the class to which GRB 170817A belongs, had been proposed as neutron-star merger products since the 1980s. The argument was circumstantial but consistent. Their durations, their host galaxy types, their locations within galaxies, and their energy budgets all pointed toward compact binary mergers rather than the depths of massive stars, which produced the longer class of gamma-ray bursts. GW 170817 confirmed the connection definitively. The merger produces a jet by a mechanism involving the rapid rotation of the merger remnant and its strong magnetic field, similar to the Blandford-Znajek process proposed for accreting black holes, in which the rotational energy of a compact spinning object is extracted electromagnetically and channeled into relativistic outflows. The jet punches through the debris cloud surrounding the merger site and, if pointed toward Earth, produces a flash of gamma radiation that can be detected across billions of light years. In the brief time before the jet is launched, the same debris cloud is being enriched with freshly synthesized heavy elements. The visible and infrared counterpart to GW 170817, designated AT2017GFO, glowed blue at first and then faded to red over a period of days. This color evolution told a specific story. The blue emission came from relatively light elements, strontium, yttrium, zirconium, freshly synthesized in the merger and moving outward at high velocity in an expanding cloud. The red emission came from heavier, slower moving material, rich in lanthanide elements whose high opacity absorbs shorter wavelengths. The spectrum of AT217 gramsvo contained the unmistakable fingerprints of R process nucleosynthesis in action.
The detection of strontium absorption features in the early spectrum was announced in late 2019, making it the first direct spectroscopic identification of a specific element being synthesized in a neutron star merger. Gold, platinum, uranium, cesium, barium. These elements do not form in ordinary stellar fusion. They form when atomic nuclei are bombarded with such an intense flux of free neutrons that they capture them faster than they can decay. A process that can only occur in the most extreme environments the universe produces, and neutron star mergers are the most extreme. A single merger event like GW 170817 is estimated to have synthesized on the order of 10 to 50 Earth masses of gold and a comparable amount of platinum, integrated over all the mergers that have occurred across cosmic time. This R process production is sufficient to account for all the heavy elements we observe in stars, in planetary bodies, and in living organisms across the galaxy. The gold in every piece of jewelry on Earth, the platinum in every catalytic converter, the uranium in every nuclear reactor. These atoms were born in collisions of dead stars, scattered across space in the expanding ejecta of kilonovae, and eventually swept up into the molecular cloud that collapsed to form our solar system. The calcium in your bones was forged in ordinary stars. The oxygen in your lungs was made in supernovae. The iodine in your thyroid and the gold in your teeth were synthesized in neutron star mergers. You are, in a literal and specific sense, built partly from the wreckage of ancient dead star collisions. The chemical evolution of the galaxy is shaped by these contributions from different stellar populations. In the earliest period of the Milky Way's history, the first generation of massive stars formed from a mixture of hydrogen and helium left over from the Big Bang, exploded as supernovae, and seeded the interstellar medium with the first heavy elements: carbon, oxygen, silicon, iron. This material was incorporated into the next generation of stars, and so on. Each generation of stars built on what the previous generation had produced, gradually enriching the galaxy in metals. A term astronomers apply to all elements heavier than helium, regardless of whether they are actually metallic in the chemical sense. The oldest stars in the Milky Way, found in the halo and in ancient globular clusters, are extraordinarily metal poor, with iron abundances 1,000 times less than the Sun's. The Sun itself formed roughly 4.6 billion years ago from material that had been processed through multiple stellar generations, accumulating heavy elements including the R process product from neutron star mergers that had occurred over the preceding 9 billion years of galactic history. Neutron star mergers occur much less frequently than ordinary supernovae, perhaps a few per million years in a galaxy like the Milky Way, compared to perhaps 1 or 2 supernovae per century. They also produce raw process elements in larger quantities per event. Whether this rare, intense source or more frequent but lower yield production sites are responsible for the bulk of R process enrichment is still a matter of active debate. Some observations of ancient metal-poor stars show R process element abundances that are difficult to reconcile with the low merger rate expected in the early galaxy, suggesting that an additional R process site, possibly collapsar supernovae, the deaths of rapidly rotating massive stars, may have contributed in the early universe. GW 170817 established that mergers are R process factories. Whether they are the dominant factory depends on questions of galaxy assembly and binary stellar evolution that remain open. Beyond neutron stars, the wider universe contains its own record holders in extremity. Among still living stars, the most massive known objects occupy a category called hypergiants. These are stars so massive that their own radiation pressure barely holds their outer layers against gravity. The star R136A1, located in the Tarantula Nebula in the Large Magellanic Cloud, carries approximately 265 times the mass of the Sun and shines at roughly 8 million times its luminosity.
It is not old enough to have existed at the time complex life appeared on Earth. Its lifetime is measured in a few million years, and it is already well into that span. R136A1 is losing mass at a rate of roughly 1 solar mass every few 100,000 years through its stellar wind, a continuous gale of plasma accelerated to thousands of kilometers per second by the pressure of its own light. The Eddington limit sets a ceiling on how luminous a star can be without tearing itself apart. Beyond this threshold, radiation pressure overwhelms gravity, and the outer layers are expelled faster than they can be replenished. Hypergiants live very close to this boundary, and it shows they are not stable in the way that main sequence stars are. They pulsate, they erupt. Stars in this mass range, like Eta Carinae in our own galaxy, roughly 7,500 light-years away, have been observed to undergo great eruptions, century-long events in which the star expels enormous shells of material, temporarily brightening to rival the most luminous supernovae while somehow surviving. Eta Carinae is surrounded today by the Homunculus Nebula, a double-lobed shell of gas ejected in such an eruption in the 1840s, when the star briefly became the second brightest in the sky. It is currently preparing for a supernova at some point in the next few 100,000 years. Red hypergiants push size to its limit without approaching luminosity in quite the same way. The largest known stars by radius are not the most massive. They are evolved red supergiants that have expanded enormously while their cores have contracted. V Canis Majoris, roughly 3,900 light-years away in the constellation Canis Major, is one of the largest known stars, with a radius estimated at somewhere between 1,420 and 2,100 solar radii. At the upper end of this range, its volume exceeds the Sun's by a factor of nearly 10 billion. It is losing mass at a prodigious rate through asymmetric outflows, not a uniform stellar wind, but a series of directed eruptions in different directions, each leaving a distinct knot or arc of material in the surrounding nebula. V Canis Majoris is expected to explode as a supernova within the next 100,000 years. It may also be a candidate for a hypernova, an explosion significantly more energetic than a standard core collapse supernova, potentially associated with a gamma-ray burst, if its core is rotating rapidly enough to launch a relativistic jet at the moment of collapse. When massive stars explode, the consequences can extend far beyond their immediate neighborhood. A supernova within roughly 25 to 30 light-years of Earth would be existentially dangerous, capable of stripping away significant fractions of the ozone layer and flooding the surface with ultraviolet radiation intense enough to collapse photosynthesis across the planet. Beyond this threshold, the effects diminish. Betelgeuse, the red supergiant in Orion, sits roughly 700 light-years away. When it explodes, and it will, though not necessarily in any human time frame, the event will produce a point of light visible in daylight and bright enough at night to cast shadows. It will be spectacular. It will not be harmful. The famous dimming episode in late 2019 and early 2020, which reduced Betelgeuse's brightness by roughly 35% over a period of weeks and prompted widespread speculation about imminent explosion, turned out to be caused by a mass ejection. The star expelled a large clump of material from its outer atmosphere, and that clump cooled and condensed into dust, blocking some of the star's light as seen from Earth. The event revealed something important about the dynamics of red supergiant atmospheres. They are not smoothly outflowing but episodically explosive, shedding clumps and sheets of material in ways that can temporarily alter the star's apparent brightness dramatically. Betelgeuse recovered and is currently burning through its remaining nuclear fuel. When it finally goes, it will be the most dramatic astronomical event visible to the naked eye in recorded history. The universe contains no shortage of near misses and reminders of how close the margins are. Systems like IK Pegasi,
a binary roughly 150 light-years away containing a white dwarf approaching a critical mass threshold, are technically capable of producing supernovae. The orbital dynamics of that system are moving it away from us faster than the relevant timescale of stellar evolution, so it poses no threat.
But it is a reminder that the ingredients for catastrophic stellar events are distributed throughout the galaxy at all distances in all directions. There is a particular strangeness to the catalogue of extreme phenomena that neutron stars represent. Black holes are often presented as the ultimate end of matter, the most extreme objects in existence. And in one sense, this is true. Nothing escapes from within their event horizons, and their singularities represent the complete failure of the known laws of physics to produce a finite answer. But a black hole, in its way, is simple. It has no accessible interior. It is characterized entirely by three numbers: mass, spin, and electric charge. It has no surface, no structure, no composition in any meaningful sense. A neutron star, by contrast, is complicated. It has a crust that can fracture, it has an ocean that can burn, it has a superfluid interior that glitches, it has a magnetic field that can rearrange itself violently and ionize the air of a planet 50,000 light-years away. It has a center whose composition we cannot determine and whose physics we do not yet possess the theoretical tools to describe. The gravitational wave detections since 2017 have introduced a new and disquieting category of compact objects: the mass gap. Between roughly 2.5 and 5 solar masses, theory predicts few objects. The maximum mass of a neutron star lies somewhere below the upper end of this range, and the minimum mass of a stellar mass black hole appears to lie somewhere above the lower end. In 2020, LIGO and Virgo detected GW90's NOAUS 814, the merger of a 23 solar mass black hole with a 2.6 solar mass companion. The lighter object falls squarely in the mass gap. It could be the most massive neutron star ever observed, or the lightest black hole ever observed. Its nature cannot be determined from the gravitational wave signal alone. In 2021, GEVWEL 200105 and GEVWEL 2115 detected neutron star black hole mergers for the first time, establishing that mixed binaries exist in the universe and that the neutron stars in those systems were consumed by black holes without any observable kilonova, consistent with being swallowed whole if the mass ratio is sufficiently extreme. The boundary between neutron stars and black holes is an observational frontier as well as a theoretical one. The extreme properties of neutron stars do not exist in isolation. They represent one point on a continuous spectrum of cosmic extremity that spans the entire universe. The coldest natural places in the universe are not the voids between galaxies, where temperatures hover around the cosmic microwave background 2.7 Kelvin. They are the Boomerang Nebula, roughly 5,000 light-years away, where gas expanding outward from a dying star has cooled through adiabatic expansion to less than 1 Kelvin, colder than the average temperature of empty space.
Moving in the other direction, the surface of Venus reaches roughly 465 degrees Celsius, hotter than Mercury, despite being twice as far from the Sun because its dense carbon dioxide atmosphere drives a runaway greenhouse effect. The surface of the Sun reaches about 5,500 degrees, but the Sun's corona reaches temperatures of 1 to 3 million degrees. Individual solar flares can briefly spike to tens of millions of degrees. The hottest stars known to science are the Wolf-Rayet stars, massive stars that have blown off their outer hydrogen envelopes entirely and exposed their hot helium-burning cores directly to space. The Wolf-Rayet star WR102, located in Sagittarius, has a surface temperature estimated at around 210,000 Kelvin and a luminosity of roughly 500,000 times that of the Sun. Its stellar wind rushes outward at nearly 2,000 kilometers per second. But living stars, however extreme, are still bounded by the physics of nuclear burning. Stellar remnants push further. Newly formed white dwarfs emerge from their formative stages at surface temperatures of 100,000 Kelvin or higher. The surfaces of young neutron stars begin at millions of degrees and slowly cool over millions of years. But the interiors of these objects, in the moments of their birth, reach temperatures that exist nowhere else in the current universe. Temperatures comparable to those of the Big Bang itself. When two white dwarfs in a close binary orbit radiate gravitational waves and spiral together, the result depends critically on their combined mass. If they merge below the Chandrasekhar limit, the product is a more massive white dwarf. If their combined mass exceeds this threshold, the electron degeneracy pressure supporting the white dwarf against gravity is overwhelmed and the object collapses, triggering a thermonuclear runaway that can incinerate the entire star in a type EAA supernova. In 2023, researchers identified an object designated J0551+4135 that appears to be precisely a white dwarf that has exceeded the Chandrasekhar limit but has not yet collapsed, held up temporarily by its rapid rotation. It is surrounded by a nebula of oxygen and neon, consistent with an origin in the merger of two white dwarfs. Its fate is fixed within some tens of thousands of years. As it loses rotational energy, it will collapse into a neutron star. For now, it spins balanced on the edge between two kinds of existence. A transitional object that occupies a category theorists predicted but had never previously observed. The planets that orbit in the vicinity of such extreme objects face their own extraordinary conditions. Neutron stars in binary systems subject their companion stars to tidal forces, X-ray irradiation, and particle winds that erode the companion's outer layers over millions of years. In so-called Black Widow and Redback pulsar systems, millisecond pulsars are in the process of ablating their companion stars almost entirely. The companion is reduced to a small, partially degenerate remnant, its mass gradually transferred to the pulsar, feeding the spin-up process while simultaneously being consumed by it. Some millisecond pulsars may have consumed their companion so completely that they now orbit nothing, isolated objects that betray the existence of a former binary partner only through their anomalously rapid rotation. The environment surrounding a pulsar presents some of the most hostile conditions in the universe. Yet neutron stars have been observed to host planets. PSR B1257+12, a millisecond pulsar roughly 1,000 light-years away in Virgo, has at least 2 confirmed planets orbiting it at roughly Earth-like distances, with masses of several times Earth's mass. These planets were the first extrasolar planets ever confirmed, announced in 1992, years before any planet around a Sun-like star was found. Their origin is uncertain. They may have formed from the debris disk left by the supernova that created the pulsar, or they may be the remnants of a companion star gradually consumed by the pulsar over billions of years. The dense, stripped cores of what were once much larger bodies, now orbiting in silence around a dead star, circling a 20-kilometer sphere of compressed matter that announces its presence 30 times per second. The future of neutron star research is being built now. The Einstein telescope, a proposed underground gravitational wave detector in Europe with arm lengths of 10 kilometers, is designed to detect neutron star mergers at redshifts of several, meaning it would observe events billions of light-years away and would accumulate thousands of merger detections per year rather than the handful per year achievable by current instruments. Cosmic Explorer, a proposed detector in the United States with arm lengths of 40 kilometers, aims for similar sensitivity.
These next-generation detectors would transform neutron-star merger astronomy from a field of rare events into a field of statistical populations, allowing the equation of state to be constrained with exquisite precision by combining the tidal deformability measurements from thousands of events. The Square Kilometre Array, the next-generation radio telescope currently under construction in South Africa and Australia, will discover tens of thousands of pulsars, including a significant population of millisecond pulsars that will extend and sharpen the pulsar timing array's sensitivity to the gravitational wave background. The Advanced X-ray Imaging Satellite proposed to succeed the Chandra and XMM Newton observatories would provide high-resolution X-ray spectroscopy of neutron star surfaces with a sensitivity orders of magnitude beyond current capabilities, enabling measurements of atmospheric composition, surface temperature distributions, and pulse profiles with a precision that would directly address the equation of state problem. There is one final dimension of neutron star extremity that deserves its place in any honest account of these objects: the way they challenge not just our measurements, but our theories. Physics rests on two foundational pillars that are individually among the most successful descriptions of reality ever constructed, but that are fundamentally incompatible with each other. Quantum mechanics governs the behavior of matter at small scales with extraordinary precision. General relativity governs the behavior of space-time and gravity at large scales with equal precision. In most places in the universe, you can apply one or the other, and the regime where the two would clash never quite arrives. A neutron star is one of the few places in the accessible universe where both are necessary simultaneously, where the quantum behavior of matter and the strong field effects of general relativity both shape the physics at the same time in the same object. The mass-radius relationship of neutron stars depends on general relativity. The way space-time curves around a dense object changes the pressure profile inside it. The properties of dense nuclear matter depend on quantum chromodynamics and nuclear many-body theory. Connecting the two requires solving coupled equations that push both frameworks to their limits. The neutron star is not merely an extreme object, it is a test case for whether our theoretical frameworks are compatible, and if not, where they break. So far, they survive. The measured radii and masses of neutron stars are consistent with what the best nuclear theories predict without obvious contradiction. But the margin for surprise remains wide enough that any major observational result could still require fundamental revision. This is why every measurement matters. The gravitational wave signal from GW170817 constrained the tidal deformability of neutron stars. Combined with the mass measurements from pulsar timing, the heaviest known neutron star, PSR J0952-0607, has been measured at 2.35 solar masses, which rules out the softest proposed equations of state, and the radius measurements from NICER, the picture is slowly narrowing. The object at the center of a typical neutron star is becoming, if not identified, at least bounded. Whatever it is something that can support roughly 2 solar masses in a sphere 11 to 13 kilometers across. That eliminates some possibilities, not all. The investigation will continue. It will continue because the objects themselves continue spinning, accreting, merging, flaring, glitching, shaking loose their crusts in quakes that ring across the X-ray sky. The universe is not finished building neutron stars, and it is certainly not finished surprising us with them. As long as massive stars live and die in our galaxy, there will be new remnants, new signals, new opportunities to press instruments against the sealed laboratory wall and listen for what the universe is willing to tell us about the deepest nature of matter. What we already know is enough to be certain of at least one thing. These objects are stranger, more extreme, more consequential, and more informative about the fabric of reality than any simple account of them can capture. They are not a footnote to the story of stellar evolution.
They are the chapter where the story becomes most interesting.
They are the places where matter reaches its final form before vanishing from the knowable world, and they spend that final form radiating, pulsing, and occasionally exploding with enough energy to be heard across the universe. They manufacture the elements that make chemistry possible, that make planets possible, that make life possible. They are among the oldest objects in the galaxy and will be among the last. Some neutron stars currently spinning in our sky were born before the solar system existed and will still be rotating faintly and slowly long after the sun has become a white dwarf and our world has cooled to silence. The formation of the binary systems that eventually produce neutron star mergers requires a specific and improbable sequence of events that begins long before any compact object exists. Two massive stars must form in close proximity, close enough that their subsequent evolution will be mutually influential. In the young universe, massive stars form preferentially in dense clusters and OB associations, regions of active star formation, where the molecular cloud has been compressed by nearby supernovae, stellar winds, or the spiral arm structure of the galaxy into dense enough concentrations to trigger runaway collapse into new stars. The Carina Nebula, some 7,500 light-years away, is one such region in our own galaxy, a churning, violent nursery of stellar formation where dozens of massive stars have already been born and some have already died. Their supernova remnants mingling with the photoionized gas around their surviving siblings. In such environments, two massive stars forming in the same molecular core will naturally be close enough to orbit each other, and the subsequent interaction of their stellar evolution will carve the binary toward compactness. As the more massive of the two stars ages faster and swells into a giant, its outer envelope may expand until it reaches the gravitational boundary between the two stars, the Roche-Lobe, and begins pouring material onto the companion. This mass transfer can be stable, gradually enriching the companion while the donor shrinks to a helium core, or it can be unstable, accelerating until the donor's envelope engulfs the companion entirely in what is called a common envelope phase. In the common envelope, the companion orbits inside the extended atmosphere of its partner, experiencing drag that slows it and causes the orbit to shrink dramatically. As the orbit tightens, the companion deposits energy into the common envelope, and if enough energy is available, the envelope is expelled and the two cores emerge in a much closer orbit than they began. This is the mechanism by which many compact binary systems are thought to form, a common envelope evolution that transforms a wide binary into a tight one, preparing it for the eventual merger. After the common envelope phase, the remaining helium core of the original primary burns through its remaining nuclear fuel and explodes as a supernova. This explosion is asymmetric. The collapsing core does not fall evenly, and the resulting neutron star receives a natal kick of hundreds of kilometers per second. In many cases, this kick is large enough to disrupt the binary entirely, sending the neutron star off as a runaway and the companion as a former binary partner moving with unusual velocity through the galaxy, in cases where the kick is oriented in the right direction. The surviving binary then consists of a neutron star and a massive companion, an X-ray binary in the making. Over millions of years, the companion evolves, transfers mass to the neutron star, or is swallowed in a second common envelope, and eventually explodes as a supernova itself, possibly producing a second neutron star and leaving the two remnants in a tight neutron star binary like the ones Hulse and Taylor discovered and that LIGO eventually heard. The natal kick imparted to neutron stars at birth is measurable from the velocities of isolated pulsars moving through the galaxy. Pulsar proper motions, measured by very long baseline interferometry at radio wavelengths, consistently show that pulsars move much faster than ordinary stars, typical velocities of several hundred kilometers per second, with some exceeding 1,000. The fastest pulsar known, PSR B2224 plus 65, moves at roughly 1,000 kilometers per second relative to the local standard of rest. It is racing through the galaxy, trailing a spectacular guitar-shaped pulsar wind nebula visible in X-rays. The bow shock of its passage through the interstellar medium bent and stretched into a shape that illustrates its speed and direction of travel. The statistics of pulsar velocities can be used to reconstruct the distribution of natal kicks, which in turn constrains the core collapse mechanism. A more asymmetric collapse produces a larger kick, and the distribution of observed kicks provides a window into the still poorly understood dynamics of the supernova engine. The interaction between a pulsar and its surrounding medium can create structures of extraordinary scale. The Vela pulsar, one of the closest and most studied, drives a wind nebula visible in X-rays that extends several light years in the direction opposite its motion. The wind, composed of relativistic electrons and positrons, inflates a bubble around the pulsar at the termination shock, the boundary where the wind's ram pressure equals the pressure of the surrounding medium. Inside the termination shock, the wind flows at close to the speed of light. At the shock, the kinetic energy of the wind is converted into the random motion of high-energy particles, which then radiate synchrotron emission across a broad range of wavelengths. The Crab Nebula's pulsar wind nebula is 3 light-years across. The Vela pulsar's nebula extends to several light-years. These structures are visible across thousands of light-years precisely because of the extraordinary power deposited by the spinning neutron star into its environment. A 20-kilometer sphere, losing rotational energy at a rate of millions of times the sun's luminosity, inflates a glowing region of space that would encompass dozens of solar systems. The X-ray emission of neutron stars in quiescent phases, when accretion has temporarily stopped, allows direct measurement of surface temperatures and therefore cooling curves. During outbursts in X-ray transients, the neutron star crust is heated above its equilibrium temperature by the compression and nuclear reactions associated with accreted material. When the outburst ends and accretion stops, the crust cools back toward equilibrium on a time scale of months to years, governed by the thermal conductivity of the crust and the heat capacity of the interior. Observing this cooling in real time tests detailed models of crustal physics, how quickly heat diffuses through nuclear pasta, how efficiently the deeper interior absorbs heat from the crust, and what happens at the crust core boundary. The neutron star KS 1731-260, which underwent a 12-year outburst before entering quiescence, has been monitored for over 15 years as its crust slowly relaxes, providing one of the longest cooling baselines available. The data are consistent with the superfluid core and the crust, with relatively efficient thermal conductivity, but the models still have adjustable parameters that have not been uniquely pinned down. The measurement of neutron star masses from binary pulsars has provided some of the most stringent constraints on the equation of state. The most precisely known neutron star masses come from Shapiro delay measurements. When a pulsar's radio signal passes close to its companion on each orbit, the signal is slightly delayed by the curvature of space-time around the companion. By fitting the delay as a function of orbital phase, both the inclination of the orbit and the companion's mass can be determined. The neutron star's mass follows from Kepler's laws. This technique was applied to PSR J0740 plus 6620, a millisecond pulsar in a binary with a white dwarf, yielding a neutron star mass of approximately 2.08 solar masses. Combined with the earlier measurement of PSR J0348 plus 0432, which has a mass of approximately 2.01 solar masses, the existence of neutron stars above 2 solar masses is now firmly established. This imposes a lower bound on the stiffness of the equation of state at high density. Any equation of state that would allow only smaller maximum masses is observationally ruled out. Whatever the deep interior of a neutron star contains, it must be stiff enough to support more than 2 solar masses against gravity.
The role of neutron-star mergers in producing short gamma-ray bursts was established long before GW 170817 confirmed it.
Short gamma-ray bursts, defined as bursts lasting less than 2 seconds, were observed to occur preferentially in elliptical galaxies and in the outskirts of star-forming galaxies, far from the active star-forming regions where the deaths of massive stars produce long gamma-ray bursts. This location preference is what you would expect from binary compact systems. They take hundreds of millions of years to merge, during which time the binary can travel far from its birthplace in a star-forming region, or the galaxy itself can exhaust its star formation and become elliptical. The identification of a short gamma-ray burst with a kilonova counterpart, suggested in a handful of cases before 2017 on the basis of infrared excess emission in afterglow observations, became definitive with GRB 17817A. The kilonova outshone every previous candidate by the quality and completeness of its data. The physics of the kilonova emission deserves attention in its own right. The process produces nuclei far from the valley of nuclear stability, nuclei so neutron-rich that they decay rapidly by emitting neutrons and beta particles, cascading down toward stable configurations. Each decay releases energy that heats the expanding ejecta from within. This radioactive heating, distributed through millions of nuclear species all decaying simultaneously, sustains the kilonova luminosity for days after the merger. The opacity of the ejecta to radiation depends critically on which elements are present. Lanthanides and actinides, elements like cerium, neodymium, and thorium, have complex electron configurations that make them extremely opaque to optical and ultraviolet photons. Material rich in these heavy elements forms what is called the red or infrared component of the kilonova. Material that contains lighter R process elements, strontium, barium, and similar, is less opaque and forms the blue component that dominates in the first hours to days. By modeling the spectrum and light curve of a kilonova, astronomers can in principle read off the composition of the ejecta and thereby measure the R process yields of the merger directly. The spectroscopic identification of strontium in ET 2017 XFO was not straightforward. The ejecta were moving at 10 to 30% of the speed of light, Doppler broadening every spectral feature into wide overlapping smears. Identifying individual elements required detailed modeling of thousands of potential transitions under extreme conditions, high temperature, high velocity, non-equilibrium ionization that have no laboratory analog. The analysis relied on atomic data computed from first principles quantum mechanical calculations, some of which had to be performed specifically for this purpose after the merger was observed, because the relevant lanthanide opacities had never before been needed in any astrophysical context. The identification of strontium required matching the observed spectral features to computed models, while simultaneously fitting the temperature evolution of the ejecta. It was detective work of the most technically demanding kind, conducted at speed because the source was fading. As the gravitational wave detector network expands and improves, the statistical harvest of neutron-star mergers will transform the field. Each merger detected is a measurement of the tidal deformability of neutron stars at the moment of merger, which constrains the equation of state. Each kilonova observed is a measurement of R process yields, constrained by the light curve shape and the spectra of identified elements. Each short gamma-ray burst, localized to a host galaxy, constrains the merger rate as a function of cosmic time and galaxy type. Collectively, these measurements will determine the equation of state, the heavy element production history of the universe, and the distribution of binary compact objects throughout the galaxy, three of the most important open problems in astrophysics from the same dataset. The gravitational wave era is in this sense not merely a new observational technique, but a new discipline. It connects nuclear physics in the laboratory, stellar evolution theory, chemical evolution of the galaxy, and cosmology into a single observational thread. The cosmological implications of neutron star mergers extend even further. GW 170817 provided an independent measurement of the Hubble constant, the rate at which the universe is currently expanding. The gravitational wave signal encodes the luminosity distance to the merger, how far away it is in absolute physical units, without requiring the chain of distance ladder calibrations that conventional methods use. The optical counterpart allowed the recession velocity of the host galaxy to be determined from its redshift. Dividing velocity by distance gives the Hubble constant directly. The measurement from GW 170817 yielded a value of roughly 70 kilometers per second per megaparsec, intermediate between the two conflicting values obtained by different conventional methods, one based on the cosmic microwave background giving about 67, and one based on local distance ladder measurements using Cepheid variables and type Ia supernovae giving about 73. The discrepancy between these two values, known as the Hubble tension, is one of the most significant unresolved problem. Gravitational wave standard sirens, as merger-based distance measurements are called, offer a completely independent path to the Hubble constant that does not rely on any of the calibrations assumed by either conventional method. As the number of detected mergers grows into the hundreds, the statistical uncertainty on the gravitational wave Hubble constant will shrink to the point where it can definitively confirm or refute the reality of the Hubble tension. The dead stars are not just telling us about nuclear physics. They are measuring the expansion of the universe. The investigation will continue. It will continue because the objects themselves continue, spinning, accreting, merging, flaring, glitching, shaking loose their crusts in quakes that ring across the X-ray sky. The universe is not finished building neutron stars, and it is certainly not finished surprising us with them. Every new gravitational wave detector brought online extends the volume of the universe surveyed for mergers. Every new radio telescope expands the senses of pulsars and pulsar timing arrays. Every new X-ray space mission deepens our measurement of surface temperatures, radii, and burst profiles. We are not running out of questions. We are not running out of objects. We are slowly, painstakingly acquiring the instruments adequate to the strangeness of what the universe has built. What happens in the immediate aftermath of a neutron star merger is itself a subject of intense theoretical and observational interest. When two neutron stars collide, the product is not immediately a stable object. The combined mass typically exceeds the maximum mass that any cold, non-rotating neutron star can support. The merger remnant is sustained temporarily by rotation, spinning faster than a millisecond pulsar as angular momentum from the inspiral is deposited into the merged object. This hypermassive neutron star is unstable. It loses angular momentum through gravitational wave emission and neutrino-driven winds, and as it slows, it can no longer support its own mass against gravity. It collapses to a black hole, possibly within milliseconds, possibly within seconds, depending on the masses involved and the equation of state. If the equation of state is stiff enough, the remnant might survive longer as a supermassive neutron star, rotating fast enough to remain stable against collapse, but eventually spinning down and collapsing as it loses rotational support. If the combined mass is small enough, the remnant might survive indefinitely as a stable neutron star, though this requires the total mass to be well below the maximum mass limit. The duration of the remnant's lifetime before collapse determines how much material is ejected and in what form. A longer-lived remnant drives stronger neutrino-driven winds, enriching the surrounding ejecta with neutrons and altering the neutron-to-proton ratio of the outflow. This ratio is the key variable determining which elements the R process produces
A more neutron-rich outflow produces heavier R-process elements.
A quickly collapsing remnant, by contrast, produces less neutrino-driven wind and more neutron-rich dynamical ejecta from the tidal tails and the collision interface. The nucleosynthetic output of the merger is therefore sensitive to the equation of state in a direct and measurable way. Stiffer equations of state produce longer-lived remnants, more neutrino-driven wind, and a different heavy element abundance pattern than soft equations of state. The kilonova light curve and spectrum contain this information, though extracting it requires modeling at a level of sophistication that is still being developed. The gravitational wave signal from the post-merger remnant, if it survives long enough to emit, would contain frequencies in the kilohertz range determined by the oscillation modes of the rapidly spinning merged object. These frequencies depend directly on the equation of state in a way that is more sensitive than the pre-merger tidal deformability. The current generation of gravitational wave detectors is not sensitive enough at kilohertz frequencies to detect this post-merger signal, even from a nearby event. The next generation of detectors, optimized for high-frequency sensitivity, would be able to detect post-merger oscillations from events within a few tens of megaparsecs. This prospect motivates a significant portion of the design choices for proposed next-generation facilities. The ringing frequency of a hypermassive neutron star could constrain the equation of state more tightly than any pre-merger measurement. Among the population of known neutron stars, a subset stands apart by virtue of its isolation and its thermal glow. 7 nearby neutron stars, discovered over the past few decades in X-ray observations, with the ROSAT and XMM Newton satellites, have no known binary companion, no associated supernova remnant, no detected radio or gamma-ray pulsations. They appear simply as hot blue-white X-ray sources glowing with the thermal emission of their surfaces. These objects, informally called the Magnificent Seven, have surface temperatures of roughly 500,000 to 1,000,000 Kelvin and are close enough to Earth, within a few hundred light years, that their thermal X-ray emission is detectable despite the smallness of their surfaces. They are the cleanest available laboratories for neutron star surface physics because their emission is not confused by accretion, pulsar wind nebulae, or supernova remnant background. The Magnificent Seven are slowly cooling, and their cooling rates provide information about their interior structure. Their spectra, however, are complicated by the possibility of surface magnetic fields strong enough to affect the thermal emission. Several of the 7 show spectral features, broad absorption lines at energies of a few hundred electron volts that have been interpreted as resonance scattering by protons or ions in the surface magnetic field, or as atomic transitions in a hydrogen or helium atmosphere modified by a strong magnetic field. Explaining these features precisely requires detailed models of radiative transfer through magnetized, dense, hot material that is still being developed. The features are sensitive to both the surface magnetic field strength and the chemical composition. And disentangling the two is one of the ongoing challenges in the field. Neutron stars are not distributed uniformly through the galaxy. They are concentrated in the disk, where massive star formation occurs. But they also escape from the disk through the natal kicks imparted at birth, populating the halo region. The total number of neutron stars in the Milky Way is estimated at roughly 1 billion, accumulated over the 10 billion year history of star formation in the galaxy. Of these, only a few thousand are currently observable as active pulsars. The rest have spanned down to periods where their radio emission is too faint to detect or are oriented so their beams never cross the Earth. The graveyard of old, cold, slowly rotating neutron stars is vast and essentially invisible. Some of them may still be detectable through the gravitational lensing of background stars, or through the rare but detectable accretion of interstellar gas. Finding this population and characterizing it would dramatically improve estimates of the total neutron star census and the merger rate.
accreting neutron stars in X-ray binary systems occasionally exhibit a phenomenon called the propeller effect.
When the accretion rate drops below a certain threshold, the magnetic field of the neutron star is strong enough to prevent infalling material from reaching the surface. Instead, the rapidly rotating magnetic field acts as a centrifugal barrier, flinging the infalling material outward before it can reach the star. The accretion shuts off, the X-ray emission drops precipitously, and the neutron star may briefly become detectable as a radio pulsar before the accretion rate rises again and the radio emission is quenched by the infalling plasma. This propeller effect is one mechanism through which accretion-powered X-ray sources transition to rotation-powered radio pulsars, and its observation provides direct constraints on the neutron star's magnetic field strength and spin rate. The connection between neutron star physics and the broader fabric of the universe extends to the question of dark matter. Some proposals suggest that certain types of dark matter particles, specifically those that interact weakly with ordinary nuclear matter, could accumulate in the dense interiors of neutron stars over long time scales, modifying their bulk properties. If dark matter particles have even a small scattering cross-section with neutrons and are trapped by the gravitational potential well of a neutron star, they would gradually build up in the core, potentially affecting the equation of state, the cooling rate, or the maximum mass. A neutron star that has captured a large amount of dark matter might have a different mass-radius relationship than a dark matter-free neutron star of the same original composition. Comparing the population of observed neutron stars with theoretical predictions could, in principle, constrain dark matter properties that are otherwise inaccessible to direct detection experiments. The neutron star interior is not only a laboratory for QCD, it may also be a dark matter detector operating continuously throughout the galaxy. Perhaps the most philosophically striking aspect of neutron star research is what it reveals about the relationship between the very small and the very large. The equation of state of dense nuclear matter, a question about the behavior of quarks and gluons, the smallest known constituents of matter, determines the size and mass of neutron stars, objects measured in kilometers and solar masses. A measurement of a neutron star's radius with kilometer precision is a measurement of nuclear physics at densities unreachable in any terrestrial experiment. The gravitational wave signal of a merger encodes information about the tidal deformability of matter at nuclear density. The quasi-periodic oscillations of a magnetar in the minutes after a giant flare are the seismic ringing of a nuclear pasta crust. The cooling of Cassiopeia A over a decade reflects the onset of quantum superfluidity in a stellar interior. These connections between microscopic physics and macroscopic observations are not incidental. They reflect the fact that neutron stars exist in a regime where the relevant length scales, the nuclear force range of roughly a femtometer, the thermal de Broglie wavelength of neutrons at millions of degrees, the gravitational Schwarzschild radius comparable to the star's actual size, all overlap in a way they do not in any other accessible environment. The star is simultaneously a nuclear physics experiment, a quantum many-body system, a general relativistic object, and an astrophysical source. Every observation probes all of these simultaneously. And the challenge of interpreting the data is precisely the challenge of disentangling these contributions from each other, while the theory of each is still being developed. This is why the neutron star is, in the deepest sense, a more interesting object than a black hole. A black hole has no material interior for physics to work in. Its event horizon marks the boundary beyond which nothing from the interior reaches the observable universe. A neutron star, by contrast, has an interior that communicates with the exterior through its surface emission, through its gravitational effect on nearby objects, through its timing properties, through its gravitational waves, and every one of these channels carries information about conditions inside. The laboratory is sealed, but it is not silent. It speaks in pulses and in X-rays, and in the minute flexing of space-time as it spins. We have only recently acquired instruments sensitive enough to hear it clearly. What we have heard so far is extraordinary. What remains to be heard, in the full sensitivity of the next generation of observatories, may rewrite significant portions of fundamental physics. The stars that become neutron stars were not built by the universe with any intent toward our understanding. They were built by gravity, pressure, and nuclear physics, driven by the same processes that made every heavy element in your body and every photon that has ever warmed your skin. They live and die in complete indifference to our curiosity. But they leave behind objects that are, by a remarkable accident of scale and physics, observable across the galaxy and across the universe. Objects whose properties are precisely the properties we need to measure to understand the deepest workings of matter. The universe did not build a physics laboratory, but it built something that functions like one. And we have had the extraordinary luck to live in an era when our instruments have become adequate to take readings from it. The census of known pulsars has expanded dramatically in recent years, driven by improvements in radio telescope sensitivity and in the algorithms used to search for periodic signals buried in noise. The Parkes Multibeam Pulsar Survey, conducted with a 64-meter Parkes radio telescope in Australia, discovered hundreds of new pulsars in the southern galactic plane. The PALFA survey at the Arecibo Observatory before the telescope's collapse in 2020 found dozens of millisecond pulsars in previously surveyed regions by using advanced signal processing techniques. The FAST telescope in China, with its 500-meter aperture, is now the largest single-dish radio telescope in the world, and its pulsar search capability exceeds all predecessors. Within its first years of operation, FAST has discovered over 500 new pulsars, a rate that will fundamentally change the statistics of the known pulsar population. Among these discoveries are extremely faint, distant pulsars that probe the interstellar medium between us and them. The pulsar's radio waves, traveling through electrons in the interstellar medium, are dispersed by an amount proportional to the electron column density along the line of sight. By measuring this dispersion, we can map the distribution of free electrons through the galaxy. And by doing so with thousands of lines of sight toward thousands of pulsars, we can construct a three-dimensional model of the galactic electron density. This model is used to estimate distances to all newly discovered pulsars, to study the turbulence of the warm ionized medium, and to locate fast radio bursts in their host galaxies. The pulsars in this use are not interesting for what they are, but for what they illuminate behind them. Beacons whose properties illuminate the medium between us and them. The gravitational wave observations of neutron star mergers have also provided a new test of the speed of gravitational waves. General relativity predicts that gravitational waves travel at exactly the speed of light. The detection of GW81700 and GRB 700817A, the gravitational wave signal and the gamma ray burst from the same event, arriving within 2 seconds of each other after a journey of 130 million light years, constrains any difference between the speed of gravity and the speed of light to less than 3 parts in 10 to the 15th power. This measurement rules out a broad class of modified gravity theories that had been proposed as alternatives to dark energy, theories that predicted a small but non-zero difference between the two speeds. In a single observation, a neutron star merger simultaneously confirmed the neutron star origin of short gamma-ray bursts, launched the era of multi-messenger astronomy, provided a measurement of the Hubble constant, constrained the neutron star equation of state, confirmed our process nucleosynthesis, and ruled out entire families of alternative gravity theories. No other single astronomical event in history has produced such a density of fundamental results. And it was caused by 2 dead stars, each smaller than a typical city that had been spiraling toward each other for hundreds of millions of years, guided by the inexorable logic of general relativity until they finally met and announced their collision to the universe in every possible channel simultaneously. The globular clusters of the Milky Way are disproportionately rich in millisecond pulsars. These ancient, densely packed stellar systems, some of them nearly as old as the universe itself, have stellar densities in their cores thousands of times greater than the solar neighborhood. In such environments, encounters between stars are common on astronomical timescales. A neutron star drifting through a globular cluster core can capture a companion through a gravitational encounter, forming a binary that was never born as one, an exchanged binary assembled dynamically, rather than through the common envelope evolution that produces binaries in the field. This dynamical formation channel explains why globular clusters have so many millisecond pulsars relative to their total stellar mass. They are efficient factories for recycled pulsars, assembling and processing binaries at a rate that isolated field stars cannot match. The globular cluster 47 Tucanae, roughly 15,000 light-years away and visible to the naked eye in the southern sky, contains at least 29 non-pulsars. Terzan Sinf, a cluster partially obscured by the dust of the galactic bulge, contains at least 39. New surveys with fast and future instruments will discover many more, and the millisecond pulsars in globular clusters will contribute significantly to the sensitivity of pulsar timing arrays looking for low-frequency gravitational waves. The same environments that assembled these pulsars over billions of years of stellar dynamics are now, in a very real sense, instruments of gravitational wave astronomy. The neutron stars we can observe are a biased sample. We find them when they emit radio waves aimed at Earth, when they accrete from a companion and produce X-rays, when they burst thermonuclearly, or when they merge and announce themselves in gravitational waves. But the vast majority of neutron stars in the galaxy do none of these things at any given moment. They are cold, dark, isolated, slowly rotating objects that emit nothing detectable at current sensitivity limits. They are the silent majority of the neutron star population, invisible not because they do not exist, but because we have not yet built instruments capable of finding them. The full census of neutron stars in the Milky Way, perhaps 1 billion objects, accumulated over billions of years of star formation, represents a reservoir of physical information that is essentially untouched. Among those billion invisible neutron stars may be objects at the maximum mass limit, objects rotating at frequencies never yet observed, objects with surface magnetic fields and regimes between the ordinary pulsar and the magnetar, and objects in dynamical states that no model has predicted. The history of pulsar astronomy is a history of discoveries that nobody anticipated. The first pulsar found by accident, the first millisecond pulsar found as a faint, unusual signal in a routine survey, the first magnetar recognized years after its discovery, when the theoretical framework finally caught up to the observations. The next unexpected object is almost certainly already in the data, waiting for a sensitive enough instrument or a clever enough algorithm to reveal it. The sealed laboratory turns slowly in the dark. We press our instruments to the wall and listen. The answer is in there, somewhere behind 20 kilometers of compressed matter, behind physics we do not yet have the language to describe. We keep building better instruments. We keep asking the question, and slowly, with each merger detected, each pulse timed, each burst recorded, each glitch analyzed, the universe answers back. Not completely, not yet, but enough to know that the question is the right one, and that the asking of it is among the most remarkable things that matter in all its compressed and spinning and exploding forms has ever done.